Welcome, and in this video we're going to talk about prime numbers. Now, naturally, you know what prime numbers are from previous studies in math. Formally, how mathematicians define prime numbers are just numbers, so an integer p. It has to satisfy the condition that it's greater than or equal to 2, and it has to have the only divisors of this prime number p are itself and 1. Okay, so then we kind of know, like, okay, 2, 3, 5, 7, etc. Those are all prime numbers, right? And we can kind of easily determine if numbers are prime if they have a few digits, but then how can you test if a number is prime if there are many digits? And that's just a question that I want you to think about. And for those of you who are interested in computer science, computer programming, computer stuff, know that that's a good question for you to tackle using a computer. Okay. But anyway, a major result of this section actually has to do with this. So if we have a prime number, and we know that this prime number divides a product of two numbers a and b, and for future reference, I call this n. You'll see the n down below for many, but in future slides we might just talk about a number n being divisible by this prime p. So a and b are integers. Then we can say that since it divides this product, it has to divide either a or b or both, right? And then more generally, if we have a number being represented as a product of more than two integers, for instance, then we say that and we know that the prime divides the number in general, then the prime has to divide at least one of the factors. And so we're going to go through the proof for the case where it's just two products, or the number can be decomposed into the product of two numbers. If you want, I encourage you to extend this idea into the case where the prime divides the number that can be represented using multiple different factors. Okay. All right. So how we're going to start is by saying, okay, well, we're going to let G be the GCD of A and P. Okay. So what we're going to show is that we're going to focus on kind of this case, and then you can just kind of swap the condition for B if you wish. So we're going to let GCD, or G, be the greatest common divisor of A and P. Okay, so then, let's see. Then we can either say that, well, either this greatest common divisor divides P, and so then that means, let's see, we have that G is equal to 1 or G is equal to P, right? So because a prime, the only thing that can divide a prime is 1 or itself, okay? All right, so we have G as the GCD. Okay, so now, and we remember this idea that the greatest common divisor, the fact that it is a divisor, it should divide A and P. Okay? All right, so we have this, right? And now, if G is equal to P, then we are done as P, which equals G, divides A, right? Okay, and that's what we wanted to show. We wanted to show that P divides A. Okay, now, well, if this isn't the case, then we have a little bit more work to do. If G is equal to 1, okay, then we remember that we can kind of use the Euclidean algorithm. Okay, we can say we can find integers u and v such that au plus pv is equal to 1. Okay, and now I'm going to do something kind of tricky. I'm going to say, let's multiply both sides by b. Okay, doesn't change equality, so then I have abu plus pbv is equal to b. Okay, and now we know, okay, now this is just a side comment, we know that p divides ab by assumption, right? Okay, and so then let's see, so this p divides that, and then certainly p divides this, right? So then both of the terms are divisible by p, and then so then this means left hand side is divisible by p. So then therefore it stands to reason that the right hand side is divisible by p. So in other words, p divides b. Okay, so we have that either or criterion that we established above. So p divides a was the condition where it was kind of this first bullet here, and then if it wasn't that case, then it was the second case where we showed that it was divisible by, or that p divides b instead. Okay, so now what you can do is extend this to this other case where we have n can be represented as a product of many different numbers. Maybe a good idea would be to work off what we had, or what we started here, just saying that, for instance, maybe take b as, well, say a is equal to a1 and b is equal to a2 up to ak, and then you might have to go through a few more cases with this. Okay, so that's kind of the idea with this proof, and we'll kind of pick up with that in the next video.